Hey folks, welcome to this new kind of video where we will do a brief overview of this new library under the Pytorch ecosystem called Torchtune. And this is mainly a trainer library. So Pytorch has been expanding its scope and it's been developing a lot of new libraries under its umbrella. There's Torchtine, there is Torchtune, and so on. And we will start looking at them in future. But today we are looking at Torchtune. So if you have used the transformers library from Hugging Face, you know that other than inference, you can also do training in the library. And the Hugging Face trainer is quite feature rich. Like you can do all sort of training, and if you combine them with other libraries like PEFT, you can do LoRA, you can do prefix tuning, you can also do distributed training because this is also coupled together with, this trainer can be coupled together with deep speed, so FSDP and all that good stuff, and also Megatron as well. So that means 3D parallelism and all that good stuff. So this is like a pretty extensive trainer, I would say. So now, like, the current state was, if you had to train a model, either you will write a trainer class in Pytorch, which is a bit painful because you have to write a lot of things from scratch. You have to take care of the parallelism and all the distributed stuff, or you just use this trainer class and you're done. So what Pytorch team did is that they implemented this library, which is still not completely stable yet. It's 0.4, so it's not like, oh, so this is 0.4, not 1.0, because it's still a new library. It's under development rather. And what they want to do is they want to make this library the go-to library for training models. And there are two models. So there's, or rather, there are two libraries. There's Torchtune and there is Torchtine. So if I open the page, I don't think Torchtine even has a documentation page, but the Torchtine is also a training library, and it supports 1D, 2D, 3D training parallelism. But the difference is that this is meant for large scale training. Like, this is meant to be a competitor to Deeps, or work together or be a competitor to Deep Speed, and probably even Megatron or the Nemo library from NVIDIA, whereas Torchtune is meant for a single device. Now, single device could also be multiple single device and multiple GPUs, but it's still meant for some low scale training. So the way I think about it, I think of Torchtune as a fine-tuning library, and the Torchtine is a pre-training library. Although sometimes even for fine-tuning, you need like massive distributed stuff. So, all right. So today we're talking about Torchtune, and this is their GitHub page. This is their GitHub page, and what version? 0.4. Okay, perfect. And they basically right now support these models. You can also add a new model. It's not too hard to add a new model. We'll just go through the code, how to add your new model. And then basically right now, the trainer, so the way they have implemented trainer are, they have these recipes. And so you can take a recipe and the model of your choice and then apply the recipe to the model of your choice. So they have the full fine-tuning. When it says devices, it means it can work on different, so when it says 1 to 8 devices, that means like one machine with 8 GPUs. I bet that's what it means. There's no reason to cut it off at 8. Then there's LoRA, you can do QLoRA, and so on and so on. And then you can also go ahead and write your own trainer recipes if you want. And there's some steps and all the good stuff. And let me, so in this video, we'll try to use this library to show like a brief training run. But let me give you a brief overview of how the package is structured. And it's quite interesting, the direction that they've taken. So remember, I talked about recipes. So these are the recipes, or these are the different trainings that we can do right now. So there is LoRA, there is full fine-tuning. In single device means single GPU, distributed means across multiple GPUs. So if I look at distributed, it will probably use FSDP. Let's see. So I don't know if it supports, oh yeah, FSDP. Yeah, that's because if you want to do other kind of parallelism, you have to look into tensor and pipeline and so on. FSDP is somewhat of a simpler form. Yeah, so these are the trainers, and if you want, these are basically fully functional trainers, which for each of them you can just pass the model and the data, and they will run the training. And these trainers utilize classes and methods defined in the package. So if you want to write your own trainer, you can go ahead and write them utilizing the utils of the package. So speaking of that, if I go to the actual package itself, and here, so here are all the different modules. Oh yeah, so it probably also does DPO and PPO. So if I go to our LLMs folder, here are the DPO and PPO losses implemented. We can look at that as an NN module, forward and loss, and all the rewards and utilities for RLHF. And if I go to training, all the things that you need for a standard training, quantization, pooling. So if I, for example, if I go to pooling, some utilities to get unmasked sequences and so on, and a bunch of other stuff. Yeah, so this is, think of it as the utilities that those training recipes need and use. Now, if I go back to our LHF, let's see if there's anything interesting in the init. Now, basically, all the classes. All right. Now, speaking of model, so now if you wanted to create your own model, basically you'll create a new folder here. So let's look at Llama 3, and the init tells you the kinds of models, that are supported. So Llama 3, we support V as in this package supports 8B, 70B, and then the LoRA versions of them. So that's that. And the model builder class basically defines the model with the various parameters. So all the model classes that we saw are defined here, and they all call this constructor with the different parameters. So we will look at the constructor. Oh, it's not here. It's probably in the model utils. No, not obviously not in a tokenizer, but tokenizer class. Let's look at the model builder and see where Llama 3 is. So Llama 3 is in, okay, so great. Llama 3 is defined in the component builders. Oh, I can see this. All right, so let's go here. So right now, obviously, there are different layers, and some are specific. And in the modules, the specific layers for a bunch of layers are already predefined, and a lot of PEP modules, which is parameter efficient fine-tuning modules, are also defined. And here we construct the model from scratch. See, multi-head attention, and so on, MLP layers and everything from scratch, and just construct a model. And if you want to apply LoRA or DORA or any of the other good stuff, that also gets applied here. So if you have a new model, you can just like implement it here or extend the classes here and implement it. So yeah, so far this library only supports a few models. It is not as extensive as the Pytorch Hugging Face trainer, because Hugging Face trainer can literally take a Pytorch model and train it however you want. So this is just Pytorch's attempt to build a trainer within its ecosystem using their own design principles and so on, which is fine. they have a neat documentation which talk about the design and how everything is like native Pytorch, and what the recipes are, how you want to use them, some examples, and yeah, there's a whole spiel about the recipes, and if you want to create your own recipe, how do you go about it, the structure, and so on. I don't think we need to look at the documentation so much, but what we will do is deep dive into one of the training recipes. And one of the training recipes that we will deep dive into is the one that I will demonstrate as well. And that is LoRA. So we want to just try LoRA on a single device. So let's look at the code for this. So basically, all recipes are a class. These are all the different parameters or other features that they take. They take in a config which is specified in a YAML file. We'll look at it. And this config basically specifies, the device, the D types, and how much you want to train for, and so on and so forth. So that's just the constructor. If you want to load a checkpoint, there are methods defined. Okay, so the model setup stage sets up a model. Basically, what setup really means is read the config, find what model we want to use, and load it up either from scratch or from a predefined checkpoint. And when I say load it up, it means like use one of those predefined classes. So for example, for Llama, it was the LoRA, DORA, Llama 8B, Llama 70B, and so on. And then load the tokenizer, optimizer, and so on. That is pretty much it. Not anything more interesting going on here. Don't care about the profiler. There are some bits about compiling the model if you want to compile it, activation checkpointing, and so on. So that's the good stuff, right? Like you don't want to write all of this from scratch. You can just use it directly over here without worrying about these features. Optimizer setup, a LAR scheduler, checkpoint saving. Okay, now I want to talk about the cool stuff, the training step. So in train, this is pretty much very similar to how you'll write a Python. And I think you see the design guidelines, because this is coming from the Pytorch team. They like to explicitly write everything. So the training step is pretty much an advanced version of the training 101 code that you would write for a sample Pytorch code, right? So for example, here in the train method, we loop over the batches, although, or rather loop over the epochs. I prefer doing it over steps, but that's fine. Get the data and compute the loss. Now here's, this might seem a bit weird because you scale your loss by the number of tokens, because you do this when you have to do gradient accumulation, because you don't want to take a mean before you have aggregated all the items. So if you're doing gradient, if you're doing accumulation of gradients, like in the, what is it called, gradient accumulation, so you'll do 2, 3, 4 forward passes and then accumulate the gradients. So you don't want, the loss function by default takes the mean, so you want to untake the mean or undo that mean computation. However, when you're computing the gradients, you still want to take the mean, so that is done manually here, and optimize it, and then you just take the step in the optimizer, do the backward, and you take the optimizer step. So, well, here they scale the gradients, so the other way around, you compute do the backward, and then you scale the gradients. It's the same thing. So, but this is like basic Pytorch code, basic code you will write for any neural network. Yeah, and the loss computation is pretty standard. Whatever loss function you've defined, just take that and compute with your logits and your labels. So So as you can see, this is like standard stuff. The good thing is, if you don't, 99% people will work in the framework of fine-tuning LoRA or DPO or any of these. So that's good. So you don't need to worry about all these low-level implementations. You use the library as is. Let me show you that. So here, I'm on Windows. This library is not supported on Windows. Like, the library is supported, but some of the dependencies, especially the quantization libraries like bits and bytes and a few other ones, what it's called Torchtune, that is not supported on Windows. So the workaround is to use WSL2, which is what I'm using, and I get like decent performance, and everything is supported there. So that's a workaround for Windows users. So let's jump into it. So here I have two folders, a YAML file, or rather one folder, and this Gemma 2 billion instruction tune version. I have the Gemma model here, and which I downloaded from the Hugging Face repo. And here's the YAML file for doing the, basically for Torchtune. So if you want to do everything, any operation begins with a YAML file in Torchtune. So the library is meant to be used for end-to-end training or fine-tuning or something. It's not meant to be used as a function that is called. Well, you can use it, you can hack around it, but the default use is you define a YAML file, you point to your data sets, and then go. So in the YAML file, you have the tokenizer, the data set. So here we are using alpaca. So I want to do PEFT. So that's why we are loading in the LoRA Gemma model. Where are we applying PEFT, the ranks, alpha, and so on, the current checkpoint that I'm loading the model from, and the optimizers, some of the parameters, some batch size, where do I want this to be in, model to be on. So I want it to run CUDA. Do I want activation checkpointing, so on, activation offloading, so on, data type, BF16. Now, if BF16 is not supported on CUDA on Windows, at least as far as I know. So that's why WSL2. So a bunch of logging steps and so on. Now, let me show you like how easy it is to trigger the training. Okay, let me show you my terminal. Actually, let me. Right. So here, so tune is the CLI that calls everything. Under the hood, when I call it run, what is it calling? Run will call the recipe. So here the recipe that I'm calling is the LoRA fine-tune distributed. And here I specify how many nodes, how many processes per node. So what that means is I'm using just one node, one machine, and I have only one GPU. And then the config file. So path, paste it, and okay, so this root is a bad, you shouldn't do that, but it's a WSL2 distribution, who cares? I can just create a new one if things go bad. All right, so let's get started. Let's see. So it's triggering torch run. This is my config that got loaded, and it's loading the model. In the new terminal, what I'll do is I will watch my NVIDIA SMI. So how is it doing? Oh, it already started computing. So you can see it's already, I don't know if you can see, but yeah, so here you can see is already training. And that's evident because I'm using 12 gigs out of my 24 gigs of VRAM. So yeah, this will run for 5 epochs. I don't know if I said the loading rate and everything correctly. So I don't care about the model that is produced, but I just wanted to show a training run. I'm going to fast forward this to when the training is done, so I can show you how the output looks like. All right, see you in the future. Okay, so it looks like the training is done. We did for 3 epochs because we had specified 3 here. Okay, so let's look at what the output is. So if I go to the output folder, I see the, so that you all can see the file sizes. Let me show you. So we have adapters which are smaller sized, 36 MB, because these are LoRa adapters. And we have the adapter configs, and then we have the regular model. So this regular model is LoRa infused. So we can use either. You can just take the adapters, add it to your model, or you can have the fused model. So see, pretty simple. Like if I wanted to use LoRa, I just had to like use the config with the right model, and I'm done. I wonder about the extensibility of this project of Torchtune. It doesn't look very customizable, like unless you edit the recipes or you create a lot of your own thing. But at that point, you might as well use the Hugging Face library or write some custom code. So, so if you want to just use some fine tuning out of the box, maybe this library is good. But yeah. So yeah, let me know what you think in the comments. And yeah, thanks for watching this video. Like and subscribe. All right, bye.